Fabio Rondinella and I am a PhD student at the University of Udine. The title of my presentation is Improved Moduli Estimation of Airport Asphalt Concrete Layer using a Machine Learning Approach based on Heavy Weight Deflectometer data. Airport runways are key assets for both developed and developing countries. Therefore, the most suitable and reliable investigation techniques are required to assess their structural integrity in order to estimate their current technical suitability as well as their remaining service life. Moreover, investigations help in deciding what rehabilitation strategies are needed according to the allocated budget. To identify the sections that require structural rehabilitation, pavement structural data are typically obtained by means of destructive or non-destructive tests. The case study regards an experimental campaign that took place at the Falcone Borsellino Airport of Palermo Punta Raisi in the period between the 9th and 29th of February 2012. This infrastructure consists of two intersecting runways, the main one named runway 0725 and the second one named runway 0220. The instrumentation used was the Heavy Weight Deflectometer HWD Dynatest 8000, a device capable of performing non-destructive tests and widely used to determine the mechanical properties of airport pavements. To simulate the effects of an aircraft's moving wheel, small pavement surface deflections are obtained by dropping a suspended mass from a predetermined height on a 30 cm diameter plate resting on the pavement surface. The magnitude of the impulse load was around 140 kN. A set of 9 geophones is able to measure the deflection induced at several distances from the loading axis, from 0 to 1,800 mm. The investigation area was 1,800 meters long and 12 meters wide, with 5 longitudinal measuring lines and 19 impact points for each line. The figure shows the deflection measured immediately below the loading plate after the impact. The highest deflections are located near the central axis of the pavement. The broad module evaluation (ROM method) was then used to determine the stiffness moduli of the surface layer impact points, starting from layer thicknesses and HWD measurements. Once estimated the pavement layers moduli, the ROM makes the theoretical deflection basin congruent with the one measured in the experimental investigation by means of an iterative procedure. A typical approach of data science, called artificial neural networks, has been used to model this challenging phenomenon. The very basic concept is to acquire knowledge from data. It is therefore a data-driven approach, not physically based. Just like the human nervous system, an artificial neural network consists of multiple neurons connected by more or less reinforced connections. Through these artificial synapses, neurons are able to communicate by processing the information and producing an output. The artificial neuron has synapses that connect the source nodes to the single neuron, a summation that adds together the various input signals, and an activation function that limits the size of the neuron output. Each input signal is associated with a certain weight, whether positive or negative, that multiplies it. The list of activation functions investigated in the present study has been provided in Table 1. Typically, neurons are arranged in layers and connected through weighted and biased connections that progressively evolve according to a learning algorithm. The input layer consists of a number of neurons equal to the number of known data, namely 6 deflection basin parameters from surface curvature index 1 to area, the homogeneous section HS, and the spatial coordinates x and y of the corresponding impact point. The hidden layer consists of a variable integer number of neurons, here set between 1 and 30. The output evaluated was the predicted stiffness moduli of the asphalt concrete. The mathematical expressions of the implemented deflection basin parameters are shown in Table 2. Rather than using the simple odd-out procedure, which produces variable performance depending on which observations end up in the train partition or in Test 1, the early stopping procedure was implemented. Data are divided into 3 partitions. The first set allows to calculate the loss function. The second one is used to control the model generalization capabilities during the training process, thus avoiding overfitting phenomena. Finally, the third one is used to evaluate the model's predictive capabilities on data it has never seen before. Another pre-processing procedure was implemented, the k-fold cross-validation. Such resampling technique works as follows. Data are randomly mixed, are divided into k partitions, here set as 5. Next, for each individual partition, the individual group is taken as validation data, while the remaining partitions are taken as training set. The model is then trained on the training set and evaluated on the validation data. A record of the validation score is kept, and then the model is discarded. This procedure is iteratively repeated 5 times. Finally, the average of the 5 validation scores is given as general performance of the model. Data augmentation technique was implemented to expand the size of the starting dataset. New synthetic data were generated, leaving unaltered the information meaning collected during the experimental campaign. Starting data were nearly doubled by interpolating known data at a midpoint between 2 successive impact points of the same measuring line. The function implemented as interpolator was the modified Akima, also known as Makima, a bicubic polynomial in each cell of the rectangular grid. Augmented data were used exclusively during the model training phase. The supervised learning process is divided into 2 distinct phases, a forward and a backward pass. After the initialization of connections weights, the forward pass begins. It consists of processing the incoming information through the neurons to compute the network's outputs. Then, the backward pass carries out a comparison between experimental targets and the predicted outputs so that Bayesian regularization backpropagation algorithm can evaluate weights correction until minimum error is reached and weights are confirmed. The metrics implemented to evaluate model performance are here described. They are Pearson's correlation coefficient R, mean squared error MSE, and adjusted coefficient of determination S squared adjusted, respectively. According to them, the best modeling results were characterized by a logistic sigmoid activation function and a 9-23-1 architecture. As shown by the remarkable values of the performance metrics, stiffness modulus predictions proved to be reliable, especially for the log SANN model. The learning process is represented on the left, with the R curve increasing up to the highest value and the MSE curve decreasing down to the lowest value. Then they both settle around constant values, proving that adding more hidden neurons beyond the threshold of the best value would only computationally weigh down the model without leading to any benefit in terms of predictions. On the right, the results of the 5-fold cross-validation referred to the log SANN model have been graphically represented. The log SANN model finally made it possible to predict the stiffness modulus at each point of the runway, thus allowing a contour mark to be realized. It provides a representation of the payment's mechanical performance at the time of HWD experimental investigation. Unlike a simple interpolation of the back-calculated modulus data, the proposed ANN model preserves the fundamental relationships between the stiffness modulus and all the mentioned variables from a logical point of view. The proposed neural computing approach has proven to be able to predict stiffness modulus at each point of the runway. It can become crucial in the perspective of airport payment management, since it allows the available maintenance budget to be optimized in order to improve both safety and sustainability of airport infrastructures. This procedure is not designed to replace traditional structural monitoring methods, but to complement them with predictive algorithms that can support maintenance operations, reducing the effort both in terms of time and costs. It has been developed with respect to Palermo runway, but it could be easily adapted to any paved area as long as deflectometric investigation results are available. For future developments, it would be interesting to implement additional information about deflections historical series. In this way, it can be determined if this methodology is suitable also for predicting payment deterioration state evolution and scheduling intervention priorities over time. Thank you for your attention.